Trigonometric substitutions. In part 1, we introduced trigonometric substitutions, and in part 2, we looked at the form a squared minus x squared. In this video, I would like to look at the form a squared plus x squared and look at the substitution involved when you see that form. The problem I would like us to look at is the problem that was generated when we were doing length of curves. Recall that we had to use Wolfram alpha because we couldn't integrate this. Now, since the focus is integration, I'm going to just take out the bounds, and you can always just put the bounds back in at the very end. Let's just focus on the actual integration. The first thing that I would do is I would rewrite the expression underneath the radical as 1 squared plus twice of x squared. Now, this is not a squared plus x squared, but rather a squared plus twice of x squared. So we're going to have to be a little flexible here. So what's our substitution going to be? It's not going to be x equals a tangent theta, but rather it's going to be twice of x equals a tangent theta. Now, use the fact that a equals 1, and the substitution that we're going to do is the substitution 2x equals tangent theta. The book handles it a little bit differently, and so you may want to look at the book to see how they do it. But I just thought I would give you another option here for solving a problem such as this. All right, so if you do the substitution 2x equals tangent theta, then what would be dx? Well, let's see. Take the differential of both sides. The differential of 2x is twice of dx because the derivative of 2x is 2. So you have twice of dx. The differential of tangent theta is secant squared theta d theta. Okay, solve for dx. Dx would be half of secant squared theta d theta. Next, we need to figure out what 1 squared plus 2x squared is. Well, 2x is just tangent. So 1 squared plus 2x squared is 1 squared plus tangent squared, which by the Pythagorean identity is just secant squared. All right, let's do the substitution. When you do the substitution, it's going to look like this. 1 squared plus 2x squared. Instead of that, I have secant squared. And instead of dx, I have half of secant squared d theta. Now, we know that secant is positive, so the square root of secant squared is just secant. And so just looking at the integrand, the radical secant squared times secant squared is just secant times secant squared, or secant to the third. And so that simplifies our integrand. All right, so this is where we are. And where do we go from here? Well, the best thing to do is to use, or the easiest thing to do, is to use a reduction formula with n equaling 3. After you use the reduction formula, you're going to have to simplify. So 3 minus 2 is equal to 1. And after you simplify, you see that most of your footwork has been done by the reduction formula. And all you have to do now is figure out what the antiderivative of secant is. Now that's just a basic antiderivative. The antiderivative of secant is log of secant plus tangent. So when the dust settles, this is what you get. Okay, so you've done a lot of work, but you're still not done. Next, we have to work on substituting back. And recall that the substitution we used was 2x equals tangent theta. Now, if 2x equals tangent theta, that means that tangent theta is 2x over 1. Let's build the right triangle with tangent theta being 2x over 1. After you figure out what your legs are, find your hypotenuse. All right. So we need to know what secant is in order to do this. In order to substitute back, we have to know what secant is. And so what's secant? Well, that's hypotenuse over adjacent. And then simplify this, and you get radical 1 plus 4x squared. So let's do a quick summary. Tangent theta equals 2x, and secant theta equals square root of 1 plus 4x squared. We're ready to substitute back. Every time you see a tangent theta, put in 2x, and then also do your secant theta. Substitute back, and this is what you get. Now, there's just a little bit of cleanup that you need to do. You're basically all done. And at this point, remember we had our bounds 0 to 2, so you would have to evaluate this at 2, evaluate it at 0, and then find the difference in order to, and you would get the exact answer instead of an approximate answer. So pretty fun. All right, take care, and please have a